Welcome to part 2 of this week's online lecture. In part 2 we will discuss the Rovibrational Spectra of polyatomic molecules. Having discussed the vibrational spectra of polyatomic molecules, I now want to discuss the Rovibrational Spectra of polyatomic molecules. The selection rules for the rotational transitions of polyatomic molecules depend on the symmetry of that particular vibration that the molecule is undergoing, whether it is parallel or perpendicular. We can illustrate what we mean by parallel or perpendicular using water. A parallel vibration is one in which the dipole moment changes parallel to the principal axis of the molecule. So, for example, the symmetric stretch leads to changes of the dipole moment that occur parallel to the principal axis. A perpendicular vibration is one in which there is a component to the change in the dipole moment that is perpendicular to the principal axis. The asymmetric stretch illustrates this quite nicely. We'll start off with the Rovibrational spectra of linear molecules. Such molecules can have either parallel or perpendicular vibrations. So what are the selection rules for a parallel vibration? Well, again, delta V can be equal to plus or minus 1, plus or minus 2, etc. and delta J can be equal to plus or minus 1 again. And so we get a spectrum with a similar appearance to that we had for diatomic molecules. We'll get P and R branches appearing in the Rovibrational band. This is known as a PR band profile, just like the classic PR band profile we saw for HCl. For HCl we saw that there was a gap missing in the middle of the vibrational band. That is when delta J would have been equal to 0, and that doesn't occur because it is not allowed for a parallel vibrational mode. For a diatomic molecule, of course, there is only a parallel vibrational mode. But for a polyatomic system, it is possible to have a perpendicular mode, for example, the bending mode. So does this make any difference? Well, delta V can still be equal to plus or minus 1, plus or minus 2, etc. But now you see the difference. For a perpendicular vibrational mode for a linear molecule, delta J can be equal to 0. So we now can get another band appearing in our Rovibrational profile. We'll have a P branch associated with delta J is equal to minus 1, and we'll have an R branch associated with delta J is equal to plus 1. But we also have a Q branch associated with delta J is equal to 0. The Q branch will be right in the center of the P and R branches, and all Q branch transitions are going to be overlapping. And we get what is known as a PQR band profile. If you've done the HCl experiment, you may well have seen this, because you may have seen carbon dioxide present in your sample. You would have noticed that you can't get rid of all the carbon dioxide in the system. At around about 2350 wave numbers, you've got the asymmetric stretch of carbon dioxide, and that had a PR band profile. But if you look down at around 667 wave numbers, it would have shown a classic PQR band profile. The Q branch appears because delta J is equal to 0. Here is the symmetric stretch for a linear molecule, this time HCN. For this vibration, we are getting a classic PR band profile because we have both the P and R branches and nothing in the center. This must be therefore a parallel vibration. Let's have a look at carbon dioxide. This is what you would have seen your HCl experiment at around 2350 wave numbers. On the left, at lower frequencies, we can see the P branch, and on the right, at higher frequencies, we can see the R branch. And right in the middle here, we can see that there is a gap. We are missing the Q branch, because in the center here, we would see a transition only if delta J is equal to 0 is allowed. Instead, that is missing. Therefore, we know that this must be a parallel vibration, and we've got a PR band profile. What about for a perpendicular mode though? Well, we have noted the selection rule is delta J is equal to 0 and plus or minus 1. This means that for a perpendicular mode we can have a P branch where delta J is equal to minus 1 and an R branch where delta J is equal to plus 1. But we can also get a transition where J doesn't change, where delta J is equal to 0. Notice, however, that for each of the R branch transitions they occur at frequencies that are higher than the fundamental frequency, and for the P branch they are at lower frequencies than the fundamental. However, if delta J doesn't change, if I go from J equals 0 to J equals 0, or J equals 1 to J equals 1, or 2 to 2, or 3 to 3, the energy gap will be almost the same. It would be slightly different because B0, the rotational constant in the V equals 0 level, is slightly different from B1, the rotational constant in the V equals 1 level. So there will be a slight difference, but it will be pretty close. And so because of that, all of these lines associated with delta J is equal to 0 are going to overlap with one another. So we would expect that the central spike associated with the Q branch would be quite intense, and that is indeed what we see. So this is what we get for the HCN bending mode. This is the bending mode of HCN, which is a perpendicular vibrational mode. So we've got our P and R branches, and in the center we've got our intense Q branch. This is a PQR band profile, and we're going to have exactly the same thing for carbon dioxide. This vibrational band is centered at 667 wave numbers. So we've got our P and R branches, and we also have got this intense Q branch where all the lines are overlapping with one another. The lines in the P and R branches are of course separated. They are not lying on top of each other. For the Q branch they are all lying on top of each other, and so you can see it is quite intense. This enables us to identify the Q branch quite easily. This is a PQR band profile, which in a linear molecule implies a perpendicular band. So this is the Rovibrational spectrum for carbon dioxide we showed at the start of part 1. We've got a PR branch centered at around 2350 wave numbers, and because the spectrum is fairly low resolution, you're not able to pick out the rotational fine structure in the bands. But at high resolution, this is what we see. And this is associated with the asymmetric stretch, of course. During the asymmetric stretch, the dipole moment is changing along the principal axis. It is thus a parallel band. But for the bending mode, the dipole moment is changing perpendicular to the principal axis, and so now we can get a Q branch appearing. And again, we cannot see the rotational fine structure unless we look at a high resolution spectrum. The reason why delta J was plus or minus 1 was because we needed to conserve angular momentum. The photon had 1 unit of angular momentum. We just didn't know if it was plus 1 or minus 1. And the angular momentum of the molecule was associated with its rotational structure, that is, which J state it was in. And so the photon, when it gets absorbed, transfers its angular momentum to the molecule, and so the angular momentum of the molecule either goes up by 1 or down by 1. That was the reason why delta J was equal to plus or minus 1. However, now all of a sudden I'm telling you that for a perpendicular band in linear molecules we can have delta J is equal to 0. So where did the angular momentum of the photon go? I will be able to illustrate this better in class on Thursday. But ultimately the angular momentum goes into the bending vibration. This type of vibration has angular momentum, and so what is happening when the photon is absorbed is that the angular momentum isn't being lost, it is just being put into the vibrational angular momentum and not the rotational angular momentum. And that's the reason why it occurred in the bending mode. For the asymmetric stretch or the symmetric stretch, there is no angular momentum associated with those vibrations. There is no breaking of conservation of angular momentum, but the angular momentum can come under many guises. Well, that was the case for linear molecules. What about symmetric top molecules? This is my rho vibrational energy. I've got my vibrational term here and my rotational term here. For a symmetric top, remember, my rotational energy term depended on both the J and K quantum numbers, and this was because we can have a difference between the rotational constants A and B. Remember, this is what the rotational energy term looked like. J can be equal to 0, 1, 2, etc. and K can be equal to 0, plus or minus 1, plus or minus 2, all the way up to plus or minus J. This is my methyl iodide molecule, and we have a symmetric stretch here where all the bonds are stretching. I would classify this as a parallel band because the dipole moment is changing along the principal axis, along the direction of the carbon-iodine bond. So for the parallel band, the selection rules again are delta V can be equal to plus or minus 1 for the fundamental, plus or minus 2 for overtones, etc. And delta J for symmetric top molecule is not only plus or minus 1, but it can also be 0 as well. This means we will see a PQR band structure. Furthermore, delta K is equal to 0. However, you can imagine that a perpendicular vibration for methyl iodide might look something like this. For the perpendicular band for a nonlinear molecule, delta V can be equal plus or minus 1, plus or minus 2, etc. And then once again, delta J is equal to 0 or plus or minus 1. But this time, delta K is not equal to 0, but is equal to plus or minus 1 and only plus or minus 1. Now this is going to lead to a significant difference in the band structure. Remember, when delta K is equal to 0, we were able to ignore the A minus B term when trying to work out what the spectrum would look like. And this was because the differences in energy between two energy levels will cancel out if delta K is equal to 0. But now, because delta K is equal to plus or minus 1, we cannot ignore the difference between the A and B rotational constants. This will lead to a difference in the vibrational structure. For the parallel band, because delta J is equal to 0 and plus or minus 1, we get P, Q and R branches. And for the perpendicular band, because delta J is equal to 0 and plus or minus 1, we will also get P, Q and R branches. So for methyl iodide, this is what the parallel band looks like. It is a very heavy molecule, so the rotational constant is very small, and so the rotational structure is very close together. We do see some overlapping lines, but we are still able to resolve the fine structure and identify the spectral lines associated with different transitions in the rotational structure of the molecule. It is clearly not as easily resolved as the carbon dioxide spectrum was. But this is a classic PQR band structure. In the middle of this band we can see a very intense Q branch. This is the perpendicular band of methyl iodide. This time we've got this kind of unresolved structure at the bottom, and then we've got these intense peaks at the top. What's going on? Well, because delta K can be equal to plus or minus 1, it means that for every initial J level there are lots of K levels we can move between. What this means is that the PQR branches are no longer on top of each other as they were for the parallel bands. And this time, because K is changing, the PQR branches are now displaced from each other. So we are still going to get PQR branches, but they are all going to be displaced from one another, so we're going to see lots of PQR branches. So this is what we are seeing here. The P and R branches are the unresolved structure at the bottom, and the intense lines on top are the Q branches. The distance between the Q branches is related to the difference between the A and B rotational constants. So, for the perpendicular bands in symmetric tops, delta V is equal to plus or minus 1, plus or minus 2, etc. And for the R branch, delta J is equal to plus 1 and delta K is equal to plus or minus 1. And this is where the issue comes in. Before, we could ignore the change in delta K. Once again, for the Q branch, delta J is equal to 0 and delta K is again equal to plus or minus 1. And again for the P branch, delta J is equal to minus 1 and delta K is equal to plus or minus 1. For every value of J, we've got many allowed values of K, and so we've got lots of PQR branches. Here are the infrared bands of nitrous oxide. There are 3 bands, and the first has a PQR band structure. The question is, can we work out the structure of nitrous oxide and assign the bands to particular types of vibration? We will assume that we know that nitrous oxide has the formula N2O. However, this could potentially mean that nitrous oxide has the structure NNO or NON. We also have to determine whether it is linear or bent. First of all, can we work out whether it is linear or nonlinear? The first thing we notice in the information given is that there are PR band profiles. If nitrous oxide was bent, all band profiles would be PQR. This means that nitrous oxide is a linear molecule. Now that we know that the molecule is linear, we also know that the first band at 589 wave numbers is a degenerate bending mode. This is because it has a PQR band profile. The only bands that exhibit a PQR band structure in a linear molecule are perpendicular bands, and for a triatomic this has to be a degenerate bending mode. Another thing to note about the bending mode is that the band is not as strong as the others. It is generally the case that bending vibrations give bands which are not as strong as stretching vibrations. This can be rationalized because stretching vibrations generally exhibit a greater change in dipole moment during the vibration. Next, we have to decide whether the molecule is NNO or NON. Well, there are 3 bands that are infrared active, and if the molecule was centrosymmetric, i.e. had the structure NON, then its symmetric stretch would be infrared inactive, and only 2 bands would be active. As there are 3 bands active, nitrous oxide must have the structure NNO. What about assigning the bands to symmetric and asymmetric stretches? Well, as a general rule, asymmetric stretches occur at higher frequencies than symmetric stretches, and so the band at 1285 wave numbers is the symmetric stretch, and the band at 2224 wave numbers is the asymmetric stretch. There is a tutorial question that determines the relative frequency of symmetric and asymmetric stretches, and we will cover this in the problem solving session on Thursday. This is the end, part 2 of this week's online lecture. Please continue on to part 3.